Thanks. Okay, so before I start, I just want to mention that everything I'm going to be saying is joint with Julia Wolf, in case I forget to say that again. So I'm going to start with just some history and some context for the problem we're going to be looking at. So we're going to start with just graph regularity. So I think of graph regularity as one answer to this question of how you can measure sort of large-scale structure in a finite graph. So you give me a finite graph, what can I do to it so that I can analyze like what's going on with it in kind of a global way? So you can use regularity lemmas. So now I'm going to give you a couple definitions, and then I'm going to state just Semiretti's regularity lemma in the graph setting, even though I know most of you have seen this already this week, but we're going to do it again. So suppose G is a graph, and epsilon is some number bigger than 0, and I take a pair xy of vertices from the vertex set V. Then I say the pair xy is epsilon regular if for every x prime contained in x, which is at least an epsilon proportion of x, and every y prime contained in y, which is at least an epsilon proportion of y, you get the following inequality. So what I have here is, this says that the density of edges between x prime and y prime is at most epsilon away from the original density of the pair you started with. So if you don't know what the density is, so the density, like d of xy, is just the number of edges between x and y divided by the size of x times the size of y. So it's the proportion of possible edges you could have. So this is saying, so the idea is that if you have a pair is epsilon regular, if it looks kind of uniform. So if you take sort of substantially sized blobs out of either side and you look at the induced graph there, you haven't changed the density of the graph much. So it sort of looks uniform when you kind of are taking pieces. Okay, so now I'm going to give you another definition. So an epsilon regular partition of a graph G is a partition P of the vertex set such that it's an equipartition, meaning every two pieces in the partition differ in size by at most 1, and all but at most epsilon k squared pairs Vi, Vj are epsilon regular, so where k is the size of the partition. So the idea here is I've broken my graph into k parts. So there's on the order of k squared pairs of parts you could look at, and this is saying that all but a very small proportion of them are epsilon regular. So all but an epsilon proportion are uniform with this parameter epsilon. Okay, so now I'm about to state the regularity lemma. So just for some notation, I'm given an integer x. W of x will denote the exponential tower of 2's of height x. Okay, so now I'm going to state the actual regularity lemma. Okay, so this says for all epsilon, there's some constant m bounded above by a tower of 2's of height, some polynomial in 1 over epsilon, such that the following holds. So for every graph G with at least m vertices, there's an epsilon regular partition, V1 through Vm, for some m between 1 over epsilon and big M at the top. So the point is, the important part is this upper bound here. So you give me an epsilon, and so that's sort of how uniform you want the partition to look. And then I know that there's some constant depending only on epsilon, so that for any graph, any finite graph, I can find a partition into at most big M pieces, which is epsilon regular. So this is interesting when the graph G is much larger than the bound M, because then it's like you're taking a huge graph, breaking it into relatively small number of pieces so that each pair of pieces you can understand in some way, in the sense that you have a density, and then you know that you know something about how uniformly distributed the edges are. Okay, so one way to think of this is that the regular partition is telling you about the approximate global structure of the graph when the graph is really huge compared to the size of the partition. Okay. Okay, so then a natural question people asked was, can you improve the regularity lemma? So for instance, must you allow for the irregular pairs? So remember, in the definition of a regular partition, we allowed for an epsilon proportion of the pairs to be non-regular. Okay. So do we have to allow for that? And on the other hand, that tower bound was sort of unpleasant. Can we get rid of that? Okay, so the answer to these two questions will be no. So, okay, so I'm going to give you a definition. A half graph of height k is a graph v comma e. V is of the form a1 through ak, b1 through bk, and given an ai and a bj, it's in the edge set if and only if I is at most j. So you could also, if you're a model theorist, this is just a particular sort of compact instance of an order property. Okay, it's an order property of length k inside for the graph edge relation. Okay, so then it's well known that large half graphs must have irregular pairs. So this is sort of the canonical example of a graph where when you go to apply the regularity lemma, you have to allow for irregular pairs. There's always going to be irregular pairs. And then on the other hand, a construction of Gower's shows that you have to have a tower type bound for the M. So neither of these two aspects of the regularity lemma can be improved in general. So that leads to the question instead, when can you improve the regularity lemma? So that's the question I think is really interesting, because this is also, we can think of this as asking, when do graphs have better than usual structure? If we think of the regularity lemma as measuring the structure, like how much global structure a graph has, this is asking when can you see the structure in, what kind of extra structure improves the regularity? Okay, so that's why I think this is interesting. Okay. Right, so that's our question. Okay, so if you're a model theorist, the appearance of this half graph is sort of suggestive that something related to stability is going on. And the idea is, so a large half graph gave us the example of when you must allow for irregular pairs. So an idea one could have is, well, maybe if we forbid half graphs above a certain size, we'll be able to ensure there are no irregular pairs. So that's the idea behind the theorem I'm going to show you. So first, we say a graph is k-stable if there's no a1 through ak, b1 through bk, so that ai, bj is an edge if and only if I is at most j. So this is just saying that G is a graph where the edge relation has no order property longer than k. So this is a theorem of Malliaris and Shelah, and this shows exactly what one would expect in terms of if you bound the size of a half graph, you have no irregular pairs. So in particular, it says that for all epsilon and k, there's some constant c, some constant n, such that if G is a k-stable graph with at least n vertices, then there's an equipartition of the vertex set such that the following holds. Okay, so first of all, the size of the partition is only polynomial in 1 over epsilon. So in the general regularity lemma, this was a tower of 2's of height polynomial in epsilon. So this is drastically better. And then on the other hand, for every pair xy in the partition, xy is an epsilon regular pair, so there's no irregular pairs. And then further, something else is that not only is every pair regular, but for every pair xy, the density is either very close to 0 or very close to 1. So in particular, it's in the interval between 0 and epsilon, or 1 minus epsilon to 1. Okay. So not only do you get rid of all the irregular pairs when you bound the size of a half graph, you get additional sort of unexpected extra structure in the sense that the partition is way, way smaller, and the pairs are sort of kind of more well behaved in that you know what the densities look like. They're either close to 0 or close to 1. Okay. Right, and so again, if you think of a regularity lemma as telling you about how much structure you have in a graph, it makes sense that in a stable setting, you would get very nice structure. Okay, so this is sort of a graph theory story, and now I want to change gears a little bit and talk about something called arithmetic regularity. Okay, so Malliaris regularity lemma is really important in extremal combinatorics. It has many applications. So here's one application, a very useful theorem you can prove using Malliaris regularity lemma. So this is called the triangle removal lemma. So it says that for all epsilon, there's a delta, so that if a graph G with n vertices contains at most delta n cubed triangles, then it can be made triangle-free by removing at most epsilon n squared edges. Okay, so the idea here, n is the number of vertices. The total number of triangles is on the order of n cubed, and the total number of edges is on the order of n squared. So this is saying if I have a small number of triangles, then I can change a small number of edges and get rid of all the triangles. So if there's very few triangles, the graph actually looks a lot like a triangle-free graph. Okay. And so this can be proved using Malliaris regularity lemma. Okay, and so then I'm going to show you an arithmetic version, which was proved in 2005 by Green. And so I guess for this talk, arithmetic will just mean this has something to do with sets in abelian groups. Okay, so we're going to be interested in understanding the structure of subsets of certain abelian groups, and in particular, we're going to be looking at finite-dimensional vector spaces over a fixed prime. Okay, so I'm going to have an analog of this triangle removal for that context. So I need to tell you like what's a triangle for that setting. So given a set A contained in Fp to the n, a triangle in A is a triple xyz in A cubed, so that x plus y plus z is 0. Okay, so that's what we'll call a triangle. So then the triangle removal lemma, arithmetic version, says for all epsilon there's a delta, so that if you give me a set A contained in this group, Fp to the n, because this should be a p, and it contains at most delta g squared, delta times the size of g squared many triangles, then it can be made triangle-free by removing at most epsilon times the size of g elements of A. Okay, so the exponents have changed a little, and that's because, okay, how many triangles are there in the possible triangles are there in this group? Well, if I know two of them, I get the third for free. So there's only on the order of the size of g squared many triangles. Obviously, there's on the order of g many elements in the group. So this is saying if I have a small proportion of the possible triangles, I can be made triangle-free by removing a small proportion of the points from the set. So it's just a little bit of a lower dimensional analog of this triangle removal lemma. Okay, and so this is sort of the type of thing which could be useful if you're interested in understanding things about subsets of these groups. And so this result was proved using something called an arithmetic regularity lemma. Okay, so, right. So what I'm going to do now is we're going to go over what a arithmetic regularity lemma looks like, and then, as the title suggests, we'll see a stable version. Okay. So now I need to tell you what is an arithmetic regularity lemma. Okay, so for the rest of the talk, P is a fixed prime, and zeta P is the primitive Pth root of unity. And so the idea is that the arithmetic regularity lemma will say that any subset of fp to the n, for any subset, there is a subgroup of bounded index such that A is evenly distributed across most cosets of the group. Okay, so again, we're no longer interested in sort of understanding, so like in the graph setting, what we wanted to do was partition the vertex set so that we had kind of uniform behavior between the parts. And so what we're interested in doing now is understand, and so that was about understanding how uniformly distributed are the edges of the graph. And so now instead we're going to be interested in understanding how evenly distributed is the set A inside the group. Okay, so this is a definition. So I'm going to go through it, but I would say if you're not familiar with this, we're going to go through an example to see sort of what it means in a specific setting. So I wouldn't worry too much. So given a function f from the group G, which from now on is fp to the n into 0, 1, the Fourier transform of f is another function f hat from the group G into the complex numbers, satisfying this equation. So on an input t, f hat outputs this sum over the elements of x and g of the terms f of x times this pth root of unity raised to x dot t. Okay. So I would say, I'm just not going to say very much about this right now, and then we're going to look at it in a specific context and see what it's telling us. But we're going to use this notion to formalize this idea of how a set can be evenly distributed across cosets of a subgroup. Okay, so fix some subset A in the group and a subgroup of the group and a single element G. Okay, how can we measure if A is evenly distributed across this particular coset H minus G? Okay, so the idea is we're going to split H minus G into parts of equal size in a special way and see how evenly distributed A is among the parts that you get. So, okay, how are we going to do this? Fix a T in the orthogonal complement of H, and then notice, so if I define for each J between 0 and P minus 1, H sub j to be the set of x and h whose dot product with t is equal to j, then this gives me a partition of h. So in particular, like if I do j is 0, this is the set of things whose dot product with t is 0, and that's a subgroup of h. And then the other hj's form the coset partition generated by that subgroup. Okay, so I get you give me this t. I get a subgroup of index p, and these are its cosets, h0 through hp minus 1. So every t like this gives me a way to partition h into the cosets of an index p subgroup. Okay. So I just translate all of this by g, and I obtain h0 minus g up to hp1 minus g, which is a partition of the coset h minus g that I'm interested in. So the idea is you give me a t, and I get some kind of well-structured partition of the coset I'm interested in looking at. Okay, so this is the type of like special partition that I'm going to look at to understand if A is evenly distributed across this. Okay. Okay, so and then how do I measure it? So the Fourier coefficient is what's going to measure how evenly distributed A is across this particular partition. Okay, so in particular, the Fourier coefficient of this means the characteristic function of the set A plus G intersected with H evaluated at T. So remember, T was the person who gave me this partition of H minus G. Okay, so indeed, let's do a computation. So here I've just rewritten the definition of the Fourier coefficient. And then the interesting thing is, okay, you do some computation and it's equal to this sum. So let's look at that. Okay, so we've got we've got a sum. So we've got some coefficients, and we're summing over the pth roots of unity. And the point is that the coefficient of the jth root of unity, the coefficient of the jth term is the size of A intersect Hj minus g divided by the total size of Hj minus g. So this is like how much of that particular piece in the partition A takes up. So it's the density of A on that part of the partition. So I've got a partition of the coset into these translates of subgroups, and then this is a sum where the coefficients are the density of A on each part. So the point is, if A was evenly distributed across the partition, these would all be about equal, all the coefficients, because the density would be about the same in all of the different parts. And so what would happen if these were all actually equal is the thing you get at the end would be 0. So the idea is if they're close to the same, if A is evenly distributed, things will cancel, and you'll end up with this sum will have small absolute value. Okay. So the idea is if the absolute value of this coefficient is large, that means that A had to be biased towards one of the Hj minus g's. So if the absolute value is large, that has to be because one of these coefficients was larger than the others. And so that's telling you that it's not evenly distributed, it's somehow, there's more of it inside one of the pieces. Okay. Right. Okay, so then, so that's sort of, so I wanted to go over that because I think this definition can seem sort of opaque if you're not familiar with working with it. But so now I'm going to define what I mean by uniformity, or so this is going to be like kind of like our notion of regularity. So if you give me a set A and a subgroup H and an element G, I say that G is epsilon uniform for A with respect to H if all of these Fourier coefficients are at most epsilon. So this is saying, this is a notion that's this is a notion for a coset of the subgroup H. So in particular, H minus G. So this is saying that this coset H minus G is epsilon uniform if for every way of partitioning into these like well-structured pieces, I always get the sort of uniform distribution across the partition. Okay, so it's saying, yeah, so each T gives me a partition, and then this quantity is measuring how well distributed the set is across that partition, and it's saying that it's always at most epsilon. Okay. So then I say that a subgroup is epsilon uniform for A if all but at most an epsilon proportion of the elements in G are epsilon uniform for A with respect to H. Okay, so there's a lot going on here. So the first notion is something specific to a particular coset, H minus G. So it's particular to this element G. And now I say that the subgroup itself is epsilon uniform if this nice property holds for almost all the elements G. Okay. Okay. Okay, so now I can state the arithmetic regularity lemma. So this says that, so this is due to Green in 2005. So this says that for all epsilon, there's some n so that the following holds. For any little n bigger than big N, so for large n and any subset of fp to the n, there is a subgroup H of index at most something, some tower of 2s of height, polynomial in 1 over epsilon. But the point is that this depends only on epsilon, which is epsilon uniform for A. Okay, so, right, so the idea is like the subgroup has this property that on most of its cosets, A is evenly distributed across the cosets in the sense that every way of cutting it up in that special algebraic way yields something, where A has about the same density on all the pieces. So there's a lot getting packed into that one definition, and so this seems to me like a strong statement. Okay, but it should look a little bit familiar in the sense that we've got this bound here and we've got this issue with there may be non-uniform elements, so it's reminding us of the normal regularity lemma for graphs. Okay, and so this is this type of statement that was used to prove that triangle removal lemma in this same paper. Okay, so now, this is sort of an arithmetic way of looking at this. In this particular case, I can rephrase it for graphs in terms of graph regularity, so I'm going to do that because I like graphs. So given an abelian group G and an A contained in G, the Cayley graph of A and G, which I'll denote gamma G comma A, is the graph with vertex set G and edge set the pairs A, B, so that A plus B is an A. Okay, so then a corollary of this formulation up here is the following. For all epsilon between 0 and 1, there's some n so that the following holds. For every little n bigger than big N, so for very large n, there's any subset A in Fp to the n. There's an epsilon regular partition of this graph, gamma of GA, with at most some other tower number of parts, such that the parts are exactly the cosets of a subgroup. So this is essentially, the point is like, okay, gamma is a graph. So I could apply the regularity lemma to it, and I would get a partition into, mostly epsilon regular parts. But so what else is going on here? And I would get a similar bound in the number of parts. But what's special here is that the parts have algebraic structure. They're cosets of a subgroup. So it's like I start with a kind of groupy graph, and at the end you get a similarly groupy type regular partition. Okay. Well, if A is really small, then you could just, the densities would just be very close to 0, and you could just take, yeah, okay. Okay, and right, so what is this group? Obviously, all I do is I take this arithmetic regularity lemma, I just take this group H, and I take its cosets, and that's a partition of the whole group, and that's the regular partition. Okay. Okay, so and then in this corollary, so okay, this is a graph regularity lemma, and and so this is an epsilon regular partition, so it may have irregular pairs, and those irregular pairs correspond exactly to the non-uniform elements from the arithmetic version. Okay, so this is all sort of suggesting what we should expect when we go to look for the stability, the stable version. Instead of looking for non-regular pairs, we're going to look for eliminating the non-uniform elements. Okay. Okay, so so then again, a natural question to ask now that you have this arithmetic version of the regularity lemma is whether you can improve it. In particular, do you have to have the non-uniform elements? So remember, in the definition of a subgroup being uniform for a set, we were allowing a small proportion of non-uniform elements. Do we have to allow for that? And then on the other hand, is the tower bound necessary? Okay, so the answer is no again. So Green and Sanders gave an example of a set A in F3 to the n, where 0 is non-uniform for A with respect to every subgroup of G. Okay, so this means no matter how I pick the subgroup, its coset corresponding to 0, i.e. itself, I look at that, A will never be uniformly distributed in the way I would want. So that means 0 is always giving me an irregular pair in the arithmetic sense. Okay, and you can if you go look at this example, it's not quite as obvious. It doesn't obvious, so when you look at, the half graph is the example of why you need irregular pairs in Semiraty's regularity lemma. It's just a half graph. It's just exactly the order property. This one, you look and it's not quite as obvious, but you look at it for a little while and you see that you can find a very large half graph inside of there. So So there's definitely instability there. So that's good. Okay. And then on the other hand, Green gave a similar style construction showing that the tower bound is also necessary, like in the graph case. Okay, so the answer to these two questions is no. So then the next natural question is instead, when can you improve the arithmetic regularity lemma? So when can you improve the bounds? When can you get rid of the irregular pairs? Okay. Okay, so here's the question. When can you improve the arithmetic regularity lemma? So the idea is when things are stable is one place where you can do it. So what do I mean by a set being stable? So you have to sort of decide what that should mean. It's obvious in the graph case, and so it's not totally obvious in this setting, but you sort of pick the most basic relation you could define out of the set, and that turns out to be the right notion. Okay, so I'll say that a set A is k-stable if there's no A1 through BK, A1 through AK, B1 through BK in the group, so that AI plus BJ is in the set A if and only if I is at most J. Yeah.
Isn't that just stability?
Yeah. 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 So this is equivalent to just saying, I think I even, i.e. i.e. the Cayley graph is k-stable. Okay. Yeah, so in the context of, seeing that reformulation of the arithmetic regularity lemma in terms of a graph regularity for this graph, then it becomes rather clear that this is the notion of stability one should use. Okay, so today what we're going to show or state is that when A is k-stable, one can improve the arithmetic regularity lemma, recovering many of the properties from the graph case. Okay, and where this is our notion of k-stable. Okay. Okay, so I need to give you some more definitions, though, to state the results. So, okay, so given a set A in the group and a subgroup H and an epsilon and a G, I say that G is epsilon good for A with respect to H if the following holds. So this is a property. This is really a property of G and H. So it's a property of you could think of it as like a property of a coset of H. So, and it's going to be if the intersection of A with H plus G is at most epsilon H, or H plus G minus A is at most epsilon H. So this means I look at this translate of H by G, and I look at A intersected with the translate. It's always, it's either really, really small, almost nothing, or it's almost everything. Okay, so that's what it means for an element to be epsilon good. And then, okay, so then, and one can see that, or one can check that if G is epsilon good for A with respect to H, then it's epsilon times P plus 1 uniform for A with respect to H. So the idea is, okay, the uniform thing, this should mean that A is evenly distributed across this H plus G with respect to all of those different partitions that I get by looking at the Fourier coefficients. But if A is taking up like almost nothing in the coset or almost everything in the coset, obviously any way I cut up the coset and look at how evenly distributed it is, it'll look about the same because it has to take up almost every piece in the partition or almost nothing in any piece. Okay, so that's the idea behind why that's true. So being good is stronger than being uniform. Okay, and then I say that a subgroup H is epsilon good. So ignore this part. So given a set A and a subgroup H and an epsilon, the subgroup H is epsilon good with respect to A if every G in G is epsilon good for A with respect to H. Okay, so if you get this really strong property about A intersecting every single coset of H, either trivially or like in almost the whole coset, then I'll say the subgroup is epsilon good. Okay, and so combining that with this observation here, if H is epsilon good for A, then every G is epsilon P plus 1 uniform for A with respect to H. Okay, so, and when that happens, I'm going to say that H is totally epsilon P plus 1 uniform for A. So remember, the non-uniform elements are like our irregular pairs. So totally uniform is kind of our way of saying no irregular pairs. And this is saying if H is epsilon good, then there's like no irregular pairs. Okay. Okay, so now I can state the main theorem. Okay, so this says that for any epsilon and k and prime p, there's some n0, so that for all little n bigger than n0, the following holds. If I take a k-stable subset of fp to the n, I can find a subgroup H of index at most polynomial in 1 over epsilon, where the degree depends on k. That's what this is saying. So it's got very small index, which is, and such that H is epsilon good for A. Okay. So there's a lot going on here, so let's sort of point out the important things. Okay, so as we said on the previous slide, because H is epsilon good for A, it's totally epsilon p plus 1 uniform. So basically this is saying there's no non-uniform elements, which we're thinking of as like our analogs of no irregular pairs. Okay, the index of H is polynomial in 1 over epsilon. So remember, in the general arithmetic regularity lemma, this was a tower of 2's of height polynomial in 1 over epsilon. So it's much better here, right, as opposed to a tower of height polynomial in 1 over epsilon. And then on the other hand, by goodness, the intersection of A with every coset of H is either almost trivial or almost the entire coset. So we should think of this as being kind of an analog to the 3 bullet points from the graph regularity lemma, where we had no irregular pairs, small size of the partition, and all the densities close to 0 or 1. So we're getting kind of all the things we would expect to get from a stable regularity lemma. Okay, so now, just because I think it's nice, I'm going to restate this for graphs in a graph version. So this is going to be a regularity lemma for the Cayley graph. So this says for any epsilon and k and prime, there's an n0, so that for all little n bigger than n0, the following holds. If I take a k-stable subset of the group, fp to the n, then there's a partition p of the Cayley graph, gamma ga, satisfying the following. The size of the partition is polynomial in 1 over epsilon. For every pair xy from the partition, xy is epsilon regular, and the density is close to 0 or 1, so between 0 and epsilon, and 1 minus epsilon and 1. And P consists of the cosets of a subgroup. So this is all looking a lot like the stable regularity lemma, or what I would get by just taking the stable regularity lemma for graphs and applying it to this particular graph, gamma. However, I'm getting extra algebraic structure in the parts, in the sense that the parts aren't just subgraphs, they're cosets of a single subgroup. So I'm getting like a group theoretic version of the stable regularity lemma. Okay, so what do I want to point out about this? There's no irregular pairs. The number of parts is polynomial in 1 over epsilon. Each pair has density close to 0 or 1. And the parts are the cosets of a single subgroup. So I like this reformulation because it's about graphs, so it's very easy to compare to the graph regularity lemma for stable graphs. And we see that it has all of these nice desirable properties that I wanted, with the addition of the coset, the pieces being cosets of a subgroup. Okay. Aha, okay, we have another corollary. Okay, so the main theorem also implies a structural condition on stable subsets. Okay, so you give me an epsilon, a k, a prime. I can find an n, n1, and a polynomial h of x depending only on k, so that for each n bigger than n1, the following holds. Okay, so suppose g is fp to the n and a is a k-stable subset of g. Then there's a subgroup h of g of index h of 1 over epsilon, so index polynomial and 1 over epsilon, and a set I of cosets of the subgroup, so that so this line here says that A is approximately a union of cosets of the group H. So in particular, I've got this set of cosets I, and this quantity here is the union of the cosets from I, and this is saying the symmetric difference of A with that union of cosets is at most epsilon g. So this is saying that up to this epsilon error, A is just a union of cosets of g. Okay, and that's a direct corollary of the previous regularity lemma. Oops. Okay, and so something I want to point out and sort of advertise for Gabe's talk coming after mine, which generalizes some of this work minus the bounds, we were able to show in the general case, using model theory and ultra products, that this g here could be improved to an h. Okay, so I think morally there should be some proof in the finite setting that also yields an h here instead of a g. Okay, but I don't know how to do that right now. So, but I just think that's interesting. So, okay. Okay, so now I just want to make a couple remarks on the proof, which I think are interesting. So I'm going to give you just sort of a high-level, vague outline of how the proof works in the graph setting. So you take a stable graph, and so it's k-stable. So the edge relation has no order properties longer than k. So then case 1, G contains a large epsilon excellent subgraph. Or so what you do is you say G contains a large epsilon excellent subgraph. So don't worry about what an excellent subgraph is, but it's sort of like being good but better. Okay, I didn't come up with this nomenclature, but yeah. Okay, and then the idea is if there was no epsilon excellent subgraph, you can kind of blow up the 2 rank on the edge relation, which is bounded by stability. Okay, so if you don't know what those words mean, don't worry about it. And then you get to get the partition of G into excellent sets, you iterate the argument. So you say G contains a large epsilon excellent subgraph. So you pull that out, and then you look at what's left over, you run that lemma again, you pull out another piece, and then you keep doing that. And then you get a partition, and then you do more work to make the parts have the same size. Okay. Okay, so this is how okay, on the other hand, so something interesting that happens is how I think these proofs compare to each other. So in the group setting, I take a subset of fp to the n, which is k-stable, and I show G contains an epsilon good subgroup of small index. And again, this proceeds by going by contradiction and saying, if not, the 2 rank of the edge relation would become too large. And here, this good is actually not as good as this excellent. So we are obtaining something slightly, even just a priori slightly weaker in this argument. So there's less work involved to some extent. Well, in some sense. On the other hand, right, so here I say similar arguments as in the graph case. However, you have to do some additional work using analytic arguments to deal with the group structure. So the point is I'm not just looking for a subgraph, I'm looking for a subgroup. So that's where you have to do some extra work to get the subgroup. So like the combinatorial argument is similar and maybe slightly less complicated, and then you have these extra ingredients you need to get the group structure. And then what's interesting is that you're done. So here in the graph setting, you had to iterate this process to get the partition, and then you had to do more work to get the parts of the same size. But we're done here because once you find a single subgroup, you automatically get a partition into the cosets of the subgroup, which automatically have the same size. So you get to leverage the group structure you're getting out of this. So you do a little more work in some places, and then you're done. And I think that's really nice. So somehow the algebraic structure is giving you some of this stuff for free. Okay. So, right. Okay, and so I'm almost done, and so I guess I'll just advertise again that Gabe and me and Anand have some generalizations to arbitrary finite groups, which Gabe's going to talk about in the next talk. So I hope everybody stays. Okay, so that's the end.
Any questions?
Can you go back to slide 15 or 16?
Oh, 16?
Okay, how much, anyway, how much N1 depends on P?
How much, sorry?
N1 depends on P.
Oh, well, it just depends on it, because, well, it's like you need the group to be like large, and the size of this is P to the N, so it's just, that's how it's showing up, is like I have the part in the argument where I'm looking at sort of like two cosets, and I need them to be above a certain constant size, and the bound on the bound, so that means that like I need P to the N to be above a certain size. So
we're going to get it to not depend on anything, but we're not going to have the polynomial bound.
Right, so if you want to keep both, you will false.
It's work in progress.
I mean, I don't think that this bound is as interesting as like this polynomial or this. Yeah. I see. But don't we know what the regularity lemma for pseudo-finite fields looks like? But okay. Yeah, it's different, right? Yeah. Okay.
Question finished today? Okay, no,
To ask, in this stable context and in the original grids context, you formulated first this arithmetic results for groups and then corollaries for Cayley graphs. Is it possible to deduce the theorems from the corollaries also?
Yeah, so I think that, yeah, I think you can go, between here and the other, and the other formulation, if I understand correctly. It's a restatement, yeah. But, yeah, well, I think the reason I think it's seen that way is that when you're not in like the finite field setting, there isn't this nice graph theoretic analog. So I think this is sort of seen as kind of wherever the arithmetic version I think is seen as more fundamental or something, because that's what generalizes. Yeah.
any other questions? Yeah.
So what if you assume an IP only?
Aha. So that's since this paper came out, that was done by some combinatorialists, Fox, Zhao, Alon, yeah. Yes, and you could also hear more about that, I guess, in Gabe's talk. But so this is something we've been thinking about a lot. Yeah.
Another question. So the subgroup H you find, can it be definable over A in some language?
So for us, the way we get it, it's not clear how to make it definable. When we do the model theoretic proof, it will be definable. So right, that's something else I'd like to understand about our argument, is how to get the group to be definable. Yeah.